All right, hello girls. We are on 4-5. We're going to start this today. There are a lot of problems for examples, but I'm only going to give you 3 problems for homework. 221, 24, and 24. These are optimization problems. So you're like trying to optimize your resources. So usually it's like you're given this many feet of fence, position the fence in such a way that your square foot of area is the biggest. So you're trying to maximize the area while minimizing the perimeter, and that type of thing, or maximizing the volume while minimizing the surface area and that type of thing. Okay, so classifications of optimization problems, they have like 2 little bullet points right here, which is like reducing to maximize or minimizing a continuous function over a finite closed interval, or you might have an infinite interval. So if I have an infinite number of resources or an infinite amount of money, maybe there is no upper limit. Okay, so that's just kind of going with like, if I only have a certain amount of resources, that's going to be a closed interval. So like this, we're trying to find maxes and mins, versus this, where I'm going from negative infinity to a positive infinity, finding maximums and minimums along those intervals, which is what we just got done doing. So just story problem context to what we got doing in this last section 4-4. Whatever. Okay, example 1. Here is my first example, and I went ahead and gave you the graph of what this looks like. So keep in mind that like on your homework assignment, you may not be given that graph, but I'm just going to kind of relate it back to what we get for an answer in this. So a garden is to be laid out in a rectangular area and protected by chicken wire fence. Okay, so I'm going to draw that rectangular area. I don't know what he's going to look like, but I'm just going to draw a rectangle. So there he is. Okay, what is the largest possible area? Okay, what's the largest possible area? So what I'm trying to find is I'm trying to find the max area. Okay, so what I'm going to get is eventually I'm going to get an equation that's going to give me a function where I'm going to find that absolute maximum, like using derivatives. Okay, so finding that absolute highest point will give me the absolute maximum area. If the garden, if only 100 running feet of chicken wire is available for the fence. Okay, so we need to give dimensions to this thing. That's all they give to us. They need to give us we need to use dimensions. Let's call him like an X and a Y. Should we do that? Okay, the 100 is the distance around there. So what do we know?
2x plus 2y.
We know the perimeter, and 2x plus 2y is the perimeter, and we know that has to be equal to 100. Okay, they're wanting us to find the maximum area. Now, how do I find the area in this case? Like the area of this thing is x times y, right? Okay, now before I find the derivative, I want to incorporate these 2 equations together, right? So I'm going to get one equation where I have both of these together. Now notice that there's an equal sign here, but we don't know what this is equal to because I don't know what the maximum area is. So when you take the equation, what you need to do is take the equation that you know, solve for one of your variables, and plug it into the other one. Okay, so, and then we'll take the derivative. Okay, so do you want to solve for x or solve for y? Y? Okay, so in this equation it doesn't matter because they're exactly the same. Sometimes it will be easier to solve for one versus the other. So if I solve for y, I have 2y equals negative 2x plus 100. If I divide by 2, y is negative x plus 50. Okay, now I'm going to plug that in here, and I'm going to distribute the other x through. Can I do that? So I have negative x squared plus 50x. You see where I get that stuff from? If I take this guy, plug him in here for y, and then distribute the x through, that's what I get. So this is my function. That is representing my area in terms of the perimeter. Make sense? Now, I want to take the derivative of that thing. Okay, I want to take the derivative. Actually, before I take the derivative, is this an open interval or is this a closed interval for what like x can be and what y can be? Closed, right? Like what's the lowest that, so we solved and have it in terms of x right now. What's the lowest number that x can be? like 0, right? Like I could have 0, which isn't going to do very good for me because if I have 0, like that's not going to be any dimension at all. But we'll say 0. Okay, what's the upper limit of what x can be? What's the highest x? Yeah. So if we're looking at this as a rectangle, if x is 50, I have 50 here and 50 here, y would be 0, right?
Yeah.
Does that make sense? Okay. And that would use all 100 feet of my fence. So I know that ultimately my x has to be a number between 0 and 50. Okay. So we are looking at that. We have a closed interval going on here. All right. Now this is just like normal. This is like what we were doing in 4-4. I want to take the derivative of this, negative 2x plus 50. I'm going to set them equal to 0. 50 equals 2x. If I move the 2x over, and x is 25. Cool. All right, so now I can do my whole like little thing here. I'm going from 0 to 25, 25 to 50, and I want to test point. What should we test? 0 to 25. 1. Okay. 25 to 50. 26.
Sure.
I'm almost tempted to do. I'm almost tempted to do like 30.
Yeah.
You know, just because it ends in a 0. You could do 26. It doesn't matter. Okay, my derivative is negative 2x plus 50. Negative 2x plus 50. Okay, if I plug in 1, 30. If I plug in 1, negative 2 plus 50, that's a plus. So increasing. Oops. 30. If I plug 30 in, would be negative 60 plus 50, so negative, so decreasing there. So I have this going on and this going on. And I'm looking just for the maximum. So I know that my two endpoints must be minimum points, right? Which we kind of knew already. Like if you 0, you're not going to have any area. So your area is going to be the lowest if you have 0 or 50, right? So 25 is going to be the highest maximum, but 25 is my x coordinates. So if x equals 25, what would y have to be?
25.
Yeah. You can plug that into the original guy.
Wait, do we have to find the max though? Or is that the max amount of area?
So here's the deal. This is the maximum x and y that will yield the maximum area. We haven't found the maximum area yet. So let's see what they're asking for. What is the largest possible area? So we're not done yet. We found the dimensions that will give me the maximum area, but what is the maximum area? Yeah, 625. Area was x times y, so 25 times 25, and that will give me 625 as the max area, which you can see. So this graph right here is the graph of your negative x squared plus 50 before we took the derivative, and you can see at 25 he's going to have the high point. You know, that's how this works out. So that is in, I don't know, are we in feet? Feet squared. So final answer, 625 feet squared. That's the maximum area using the dimensions 25 and 25. Now, you guys probably already knew that. If I want to maximize area and minimize perimeter, and I'm just looking at a rectangle, the maximum area will occur when that thing is a square, right? Okay, now, when you incorporate other things into play, which I think we've seen before, like let's say I have a river along the side here, and I don't need that fourth side of fence, that does change things a little bit. So like this would be like 2y's but 1x. Does that make sense? Okay, that does change it a little bit. So it's not going to be a perfect square in that case to maximize your area because you are missing a third side. Or there was one time where we had like, they wanted like this type of thing going on where they had like 2 pins, but then like that area, they want to maximize the area. We would have 3 y's and 2 x's. Does that make sense? So when they add in other elements besides just an x and a y and an x and a y, it might not be a perfect square. Make sense? Yep. Okay, so there's that. All right, let's go on. These are your steps. So draw an appropriate figure, blah, 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 find the formula. You're going to eventually at some point take one of the equations and plug it into the other one and then find the derivative and do that stuff. Okay, let's go to example. What do we want to do? Actually, we're not going to have time for example 2. Let's stop there. Okay, there you go. We'll continue on tomorrow. Okay, all right, goodbye girls.